Dear students, welcome to the problem solving session on Cauchy integral formula part 3. At the first two videos, we learn all the basics and then we see the formula for Cauchy integral theorem and Cauchy integral. At the part 1 video, we solve problems which consist of exactly one singular point. Maybe it lies inside or lies outside. In the part 2 video, we started learning how to solve the problem which has more than one singular point. At example 4, we see both singular point lies outside C. In example 5, one singular point lies outside C and the other singular point lies inside C. In example 6, we see both the singular points lies inside C. But something is common in all the 6 problems. We see my given region is simply mod Z is equal to some radius R. You can see the first video also. Everywhere we have mod Z is equal to some radius 1, 3, 2, etc. In this case, it is very easy to find a singular point Z equal to 1 or Z equal to 2 or Z equal to 3, etc. whether it lies inside or lies outside. By drawing the circles, we can easily identify the singular points whether it lies inside or outside C. That's why in this session we took a different problem, integral over C z square plus 1 divided by z square minus 1 dz. The region is modulus of z minus 1 equal to 1. In earlier problems, we write mod z equal to 2 means we simply say the center is 0, 0 and the radius is 2. But in this case, we cannot write like this. We have to find the center and radius. And then we have to check whether the singular point lies inside or lies outside C. Let us solve this problem. As usual, step 1, we have to find the region. Mod z minus 1 is equal to 1. We know that z is x plus iy, and rearranging the term, we get x minus 1 plus I into y is equal to 1. We know the formula modulus of a plus ib is square root of a square plus b square. Therefore, x minus 1 whole square plus y square is equal to 1. Now taking square on both sides, we get x minus 1 whole square plus y square is equal to 1 square. Therefore, the given region modulus of z minus 1 equal to 1 is a circle with center 1, 0 because the general form is x minus a whole square plus y minus b whole square equal to r square. There the center is a, b. Here a is 1, b is 0 and the radius is going to be r, that is 1. So simply mod z minus 1 equal to 1 is a circle with center 1, 0, radius 1. Now we can easily draw this figure. First we mark the center, then radius is 1. So I can mark the point 2, 0 and 0, 0. Easily we can draw the circle and we can shade the region. Step 2, singular points. Take the denominator z square minus 1 equal to 0, that is z minus 1 into z plus 1 equal to 0. Therefore, the singular points are 1, minus 1. Luckily, in this problem we can easily verify this. Z equal to 1 means the point 1, 0, it lies inside C, and z equal to minus 1 means minus 1, 0. Obviously, it lies outside C. But my recommendation, whenever the region is not easy, like mod z equal to 2 or mod z equal to 4, better we can use the modulus technique. For this, just consider the given region as it is. Now, substitute each and every point. At z equal to 1, substitute here in the left hand side of the given region. So, mod z minus 1, that is equal to 1 minus 1. It is equal to 0. Now we find our left hand side value is 0. Next we have to compare this value with my right hand side. My right hand side value here is 1. So we have to compare 0 and 1. Now we have to write whether it is less than 1 or greater than 1. Since 0 is less than 1, I can immediately say z equal to 1 is the singular point lies inside C. You can see the typed version. Similarly, for z equal to minus 1, again I will substitute in the left hand side of the given region. We get minus 1 minus 1. So modulus of minus 2 is 2. It is very obvious 2 is greater than 1. Therefore, z equal to minus 1 lies outside C. So this is the best way when my region is little complicated. If your region is simply mod z equal to 3, mod z equal to 1, etc., by seeing the figure I can easily find whether it is lying inside or outside. If you are confident, you can identify directly or use this technique to find whether the singular points lies inside C or outside C. Next we do step 3. First write the singular point and then as usual take the quotient as capital I. Now see the numerator, it is z square plus 1. It is a polynomial. We know polynomials are entire functions. They are analytic everywhere. So z square plus 1 is analytic inside and on C. It is very obvious. Just now we see z equal to minus 1. That means z plus 1. We should be very careful in choosing here. Z equal to minus 1 means when we choose in the problem it is z plus 1. Z plus 1 lies outside C. So it will not affect the analyticity. So I will take z square plus 1 divided by z plus 1. This function is analytic both inside and on C. So I will consider this function as f of z. I cannot take z minus 1 because z equal to 1 is a singular point lies inside C. When we apply 1, it is not analytic. Therefore, my small f of z is z square plus 1 divided by z plus 1. Since both are analytic, we can easily write f of z is also analytic inside and on C. Next, we have to rewrite my capital I. As I said earlier, whatever the function which are analytic, we take it to numerator. Here f of z is analytic, so we can write this as z square plus 1 divided by z plus 1 in the numerator. But in the denominator, z minus 1 is singular point lies inside C. So I will keep this in the denominator. Now easily we can apply Cauchy integral formula. Comparing the formula, we can find the solution for the given problem. My step 4 is Cauchy integral formula. Comparing f of z with the formula and the singular point, we can easily write capital I is equal to 2 pi I into f of 1, where f of z is z square plus 1 divided by z plus 1. Now substituting z equal to 1, we get 1 square plus 1 divided by 1 plus 1. 2 by 2, it is going to be simply 1. Therefore, my f of 1 value is 1. Substituting in I, we get 2 pi I into 1. Therefore, my final solution is capital I is equal to 2 pi I. Hope you understand, students. Next, we are going to see one more interesting problem. The given region is modulus of z minus I equal to 2. And here we have singular points with higher order. So let us crack this problem. As usual, first draw the figure. For this, let us find the center and radius. We know that z is x plus iy. Rearranging the terms, we get x plus y minus 1 into I is equal to 2. Modulus of a plus ib is equal to square root of a square plus b square. Therefore, we can rewrite this as square root of x square plus y minus 1 whole square is equal to 2. Squaring on both sides, we get x square plus y minus 1 whole square is equal to 2 square. So my center is 0, 1 and my radius is 2. So we can mark the center 0, 1 and radius is 2. So I can mark the point as 2, 1. Here 0, 2, we can mark this as 0, 3 and we can draw the circle. Next we are going to find the singular points. Make the denominator 0. We get z plus 1 whole square equal to 0. Z minus 2 is equal to 0. So we get z equal to minus 1 and z equal to 2. Here we don't bother about the order. even it is z plus 1 whole power 100 equal to 0, we simply write only one singular point, that is z equal to minus 1. Since the given region is little complicated, it is not like simply mod z equal to some or. Better we can substitute the points in the region and we can check whether the point lies inside or outside C. So the given region is modulus of z minus I equal to 2. So I'll take the point z equal to minus 1. We'll take the LHS. Modulus of z minus I, that is equal to modulus of minus 1 minus I. Just now we see the formula. Modulus of a plus ib is square root of a square plus b square. Therefore, square root of minus 1 whole square plus minus 1 whole square, it is going to be square root of 1 plus 1 root 2. Square root of 2, use your calculator, it is 1.414. Now we have to compare this 1.414 with the right hand side of the given region. So it is less than 2. If it is less than 2, then the point z equal to minus 1 lies inside C. We can see the typed version. Next, at z equal to 2, similarly take the LHS. Modulus of z minus I, that is equal to 2 minus I. Then we use the same formula. Modulus of a plus ib is equal to square root of a square plus b square. So square root of 2 square. The coefficient of I is minus 1. So minus 1 whole square is equal to square root of 5. Now we have to compare our LHS with the RHS value 2. Use your calculator. It is very obvious. Square root of 5 is greater than 2 because square root of 4 is 2. Therefore, we can conclude that z equal to 2 lies outside C. So in this problem, one point lies inside and the other point lies outside. We can easily tackle it. So again, I'm just recalling you, if the region is simply mod z equal to some or, then you can easily find the singular point by checking the figure. If it is little complicated like z plus 1 minus I, z plus 2 minus 3I, etc., then using this technique we can easily found whether the point lies inside C or outside C. Next, step 3, write the key points. Z equal to minus 1 lies inside C, Z equal to 2 lies outside C. Now write my question as capital I. Next we are going to deal with numerator. We know that Z minus 1 is polynomial and it is entire function. It is analytic everywhere inside and on C. Coming to the denominator, Z equal to 2 is the singular point, lies outside C. Therefore, Z minus 2 will not affect the analyticity. So we can take Z minus 1 divided by Z minus 2 as my f of Z. And we cannot take z plus 1 whole square because z equal to minus 1 lies inside C. So when I substitute, it is undefined. Therefore, my f of z is z minus 1 by z minus 2 and it is very obvious it is analytic inside and on C. Next we can rewrite capital I. Since z minus 1 divided by z minus 2 is analytic, we assume this as my f of z. We'll take this to numerator. We get z minus 1 by z minus 2. In the denominator, we have z plus 1 whole square dz. So we can rewrite this as integral over C f of z divided by z plus 1 whole square dz. It looks like the form Cauchy integral formula for higher order. Now we have to simplify this further in the proper format. So integral over C f of z. This z plus 1 I can rewrite this as z minus of minus 1 whole square dz. Now this is perfect with my formula integral over C f of z divided by z minus a whole power n plus 1 is equal to 2 pi I divided by n factorial nth derivative of the function f of z, substituting the value a. Now let us apply the formula. Since my order is 2, I can write the formula as integral over C f of z divided by z minus a whole square dz is 2 pi I divided by 1 factorial into f dash of a. Now comparing my question with the formula, we see A is equal to -1. Therefore, capital I is equal to 2 pi I by 1 factorial. 1 factorial is simply 1, f dash of -1. Next, we have to find the value of f dash of -1. f of z is z minus 1 by z minus 2. Now we have to apply u by v rule. V square v du minus u dv. Therefore, my f dash of z is z minus 2 whole square. I am considering z minus 1 as u and z minus 2 as v. v du z minus 2, when I differentiate z minus 1, I get 1 minus u dv. Keeping z minus 1, differentiating z minus 2, we get again 1. So that is equal to z minus 2 minus z plus 1 divided by z minus 2 whole square. Z and minus z get cancelled. Minus 2 plus 1 is minus 1 divided by z minus 2 whole square. Therefore, my f dash of z is minus 1 by z minus 2 whole square. Now I have to find f dash of minus 1. Minus 1 divided by minus 1 minus 2 whole square, that is minus 1 by minus 3 whole square, it is minus 1 by 9. Therefore, f dash of minus 1 is minus 1 by 9. We have to substitute this in capital I. Capital I is 2 pi I into f dash of minus 1. So 2 pi I into minus 1 by 9, that is minus 2 pi I by 9. This is my final answer. In this session, we solved two problems, that is example 7 and 8. In both the problems, my region is totally different. We have modulus of z minus 1 is equal to 1 and modulus of z minus I equal to 2. After finding the singular point, it is essential to check whether the singular point lies inside C or outside C. I'm just considering example 7. Now we have to take the left hand side. Suppose if A is the singular point, now substitute A in the left hand side. Simplifying this, we get a value. Now we have to take the RHS of the given region. Here it is 1. We have to compare the calculated value with the RHS. If the calculated value is less than my RHS, here it is 1, then we say A is the singular point, lies inside C. If the calculated value is greater than my RHS, that is 1, then we say A is the singular point, lies outside C. Hope you understand.
Thanks for watching. Hope you found this video helpful. Subscribe to our channel and share it to your friends. See you in the next video. Bye bye.